Okay, everyone. I was just reminded that I'm the chair for this session, so apologies for the delay. So we'll get started with Makana, who will tell us about beats of the universe. Please.
Hello, Kako, everybody. I'm excited to be giving this talk at this part of the symposium, since everyone has already heard how cool and impactful Lisa will be once it launches, and what sort of sources Lisa hopes to detect. And blink. There we go. One of the sources Lisa is going to be very sensitive to are these extreme mass ratio inspiral systems, or EMRIs. And again, we've heard many cool talks about how EMRIs are going to be important, what types of science we can get from them. What I want to highlight, just to sort of set the tone for my discussion, is more the precision science associated with EMRIs. And in the sense that EMRIs are almost like these cosmological metronomes, in that they have these very precise prescription for what their waveform should look like. But most likely we're not going to see perfect EMRIs, and they're probably going to be perturbed. And much like a metronome, if you do something very small to the actual calibration of it, you'll immediately hear the change in the tick. And very similarly for EMRIs, they're also going to be sensitive to these perturbations. A lot of these perturbations will probably average out, but not all of them, and I'll go into detail what I mean by not all of them. But this is sort of the big why, like, do we care about this, right? EMRIs are going to be very sensitive to these perturbations, and being able to tabulate and account for them in our waveform templates will allow us to discern these astrophysical environment impacts on the EMRIs, or maybe hint to some modified theories of gravity. So where do we expect to see EMRIs? This artist rendition of an EMRI is typically what we've seen all week. And normally we don't see EMRIs just kind of coasting in the universe with a supermassive black hole and one compact partner. This is what the galactic center looks like to this artist. And the idea is that EMRIs are typically going to be situated near other nearby orbiting systems. And so if we can account for how these nearby orbiting systems are going to perturb this EMRI, then we can figure out how this is going to impact the actual orbit and then impact the subsequently detected gravitational waveforms. So what types of perturbations am I going to be looking at? I'm going to be looking at resonant perturbations, and it's the same ones you've seen in the sort of celestial mechanics flavor, where satellites or on planets or sometimes ring systems can exchange energy and angular momentum, and it's these types of perturbations, these resonant perturbations, that don't necessarily average away over the many cycles that these EMRIs will complete during its lifetime. So what do I mean by resonant? So I'm looking at bound orbits around this Kerr black hole, these spinning black hole spacetimes, and the idea is that you can describe the motion of these orbits using three fundamental frequencies, right, in the principal directions. Frequencies, Alejandro. And the fact that you have two bodies that are going to be, in this system interacting, now we have 6 fundamental frequencies we can put together. So really the resonance condition is just a statement of what are the sort of integer combinations I can take for one body's orbital frequencies and match them to a different set of orbital or integer combinations of the other body's orbital frequency. So that refines the question a little bit more, and this is going to be the question I'm hoping to address today, which is when and how do dynamical perturbations affect EMRIs near resonance? And I want to do that using 3 points. I want to first cover a little bit of what people have already done to address this problem in this sort of specialized case, and then discuss where our formalism comes in and not only expands on it, but generalizes the approach. How do we set up and actually run our pipeline and get results? And what do those results look like in the context of the current literature? So here's our EMRI again. Hopefully people can see this sort of red curve. I'm going to go here because I sit on this end and no one ever points to this one. There's that little red curve for everyone asking. This could be hard. The reason why I do this is because the typical way people have solved these sort of resonant interactions to EMRIs is in the context of a static tidal field. So the picture is you have this orbiting system, this body that's relatively far away from the EMRI. By far, what I mean is the time scale in which this outer body is evolving is much larger than the time scale of the EMRI itself. And so what you essentially say is that the EMRI sits in this external tidal field that's relatively static. Oh, oops, wrong way. Our work does the sort of generalization of now bringing that perturbing body closer to the EMRI. So now its time scale is comparable to that of the EMRI's evolution time scale. So now the EMRI, in this case, sits in this sort of time-dependent or dynamical tidal field. So this is sort of the big picture I hope everyone walks away with today, right? People have studied the far away version a lot. We are addressing this nearer body approximation, and then how do we stitch the two pictures together? So the setup goes as follows. First, we want to set up the actual orbital configurations of the inner body, the EMRI, the outer body, the perturber, and I'm going to go between the vernacular inner and outer. We specify what is the gravitational wave amplitudes that they're going to use to interact and exchange energy and angular momentum once they satisfy this resonance condition. And then when we compute what that resonance exchange is, we're going to see how do they change or impact the orbital quantities. So I typically work in this space, in this phase space of the action variables. The thing that most people care about is the sort of related quantities, which are these flux quantities related to the energy, Carter constant, and angular momentum that describe the orbit. And ultimately, how does that impact the phase of the, I'm going to go to all of them, the phase of the associated gravitational waveform. I'm just going to talk about this section, though, because I think this is the most interesting. So I'm not even going to go through the derivation of how we got to the resonant exchange. I kind of want to talk more about when you do complete the derivation, what's the physical picture that is telling us to, what's happening during this interaction. So here's this artist's rendition again of our EMRI. So there's the EMRI system. In the inside, you have this dynamic perturber on the outside. The key thing is that both of these bodies are going to make gravitational wave modes towards the black hole and going far from the event horizon. What we find is that only certain combination of modes from the perturbing body will actually affect the EMRI at resonance. And so what that means is you can replace the third body altogether, or the perturbing body altogether, and using conservation of energy, you can reconstruct the necessary set of modes to interact with the EMRI. So we've effectively reduced the problem to this sort of hierarchical triple system problem to now just being the EMRI is undergoing a resonant response due to some sort of external gravitational wave, like laser, if you want to think of it that way. And the reason why I say that is because now we have this expression, and I don't want to just flash math at you for no reason. This is the expression that tells you what are the combination of gravitational wave modes and the other necessary scattering data you need to compute the actual change in these orbital quantities. This expression here captures those effects for generic perturbing orbits. So this is the expression, and it's kind of the backbone for the rest of this talk. So no one has really done, and please someone share if I missed it, but so far there's no work being done in the dynamic tidal resonance regime. People have done a lot of static tidal resonances, and so what we wanted to do first and foremost with a new tool is make sure this tool agrees with the current set of literature. So this plot right here is a set of tidal torques and changes in Carter constant. It's the change in these orbital parameters as a function of eccentricity, but they're all for static resonances. And so what we did was that we said, okay, let's take our perturbing body, originally, we can put it wherever we want, but we'll start close to the EMRI, and we'll move it further and further away till basically the evolution of it is negligible and it looks like a static tidal field. And what we find is that our dynamic code converges to the static results that we typically see in the literature pretty rapidly. And so that makes me happy because it's like, okay, we're on the right track. Our code reconvenes with what we expect in the static limit. The next thing we wanted to do was then analyze a slew of resonances. So this table highlights the sort of semi-major axes and black hole spins that we sampled to build these orbits. We studied about 142,000 resonances, and we found very interesting things, and I can't go through all of them. I'll go through one specific subset and example. So this plot here highlights the relative change in those orbital quantities crossing resonance. So it's the fractional change. The takeaway from this plot is follows. We studied a lot of resonances. There they are on the y-axis. But you notice on the x-axis, there are relatively small changes in these phase space variables. And what that tells me as someone who applied this perturbation theory method is that it seems like the perturbation theory holds up. We don't enter a resonance crossing where the action variables are going to undergo a non-perturbative change. I don't think. We got to see. There's no theorem that was proved for that. It's just after 142,000 cases, nothing broke. So that makes me happy. And we can then go from the changes in the action variables to the changes in the phase. And same thing, we studied a lot of resonances, and we see that most of those changes are small. But not all of them. There does exist a region where you get changes that are of order, 0.01, 0.1 radians. which depending on how you want to view, where on the LISA sensitivity curve you are, that's something LISA will be sensitive to. And what that tells us is that the sort of perturbative changes in the action variables could allow non-perturbative changes in the phases, meaning that our perturbative method might be robust enough to handle all these cases and still account for detectable changes in the phase of the waveform. So I hope the big takeaway for everybody today are at least 3 things. For the first time, we have this dynamic calculation and code that allows us to capture the phenomena that the static community has worked very hard for to account for these effects, and we also account for these effects as well. It seems like after over 100,000 resonance studies, the perturbation method holds. I'm sure someone could cook up a set of initial conditions without break, but so far we haven't. And perturbative changes in these orbit quantities could still lead to non-perturbative effects in the phase itself. So to kind of wrap everything up, EMRIs and LISA are going to change the way we study the physical universe and the way we approach gravitational wave astronomy. And LISA is going to be this giant antenna, right? It's not a telescope we can look and resolve a single source. It's going to hear all these signals at once. And as the other EMRI talks we heard all week talk about is building the waveforms, the base template waveforms are difficult. We also got to add all the necessary physics and bake it in there so that we can account for possible changes in the waveform. So we can ultimately make the distinction between unaccounted astrophysical environmental effects on the EMRIs or true modified theories of gravity. Mahalo for your time, and I'm happy to take questions.
Questions? Yep.
Sorry, this is the first time in this room. I didn't know where the mics were. Could you just flash up that table again of the 142,000?
Oh, wrong way? We're getting there. There we go.
So those, the semi-major axes are those like in gravitational radii? They look very large.
Yeah, so those are in black hole mass. Yeah, so in units of the supermassive black hole mass, which, our units we set to 1. We did put a constraint so we don't look at collisions. So we wanted to only study gravitational perturbations. So we just, we looked through the literature, and I think we came up with some restriction of the apocenter, or the point of furthest from the supermassive black hole and the outer body's closest point of approach aren't within some factor of unity with respect to one another.
Okay, so then are these, I guess I did not picture, they are evolving from this initial separation?
Yes.
So that's how they're going through all these different resonances. Okay.
Exactly.
Okay, thanks.
Good question.
Have a question?
Hi. Thank you. I had one question, and then I thought of another one in the middle of this whole thing, but I'm going to go with the first one. So a lot of what people have been talking about during this conference are these nuclear clusters, where you have all these big swirling things. And I know that's a much more complicated problem than what you're working on right now, but based on the sort of research that you've done, do you think, is it possible, can you just sort of stack these sort of individual perturbations on top of each other and just assume you can get a signal based on that? Or would this combination even be significant? Would there probably just be sort of one major perturber?
My guess is in the linear regime, you could stack them. Now again, linear perturbation theory, nonlinear theory, probably not true necessarily, when you compare the two. I want to say at least in this linear regime, you could stack them, right? So now the question, like you mentioned, which perturbation is going to dominate over another? I think that will really just depend on the nature of the resonance, the nature of the orbits when they enter resonance, which I think this work could address the sort of tidal resonance argument, but in terms of these other possible, I guess, n-2 body effects. I'd also imagine the further you are away, assuming, again, no collisions sort of things, they would get less and less appreciable because they're further and further out on this, these concentric shell sort of arguments. So to answer your question, I think we can address part of it in regards to these nuclear clusters, but I don't think we can capture all the phenomena just with this.
then can do just like a much shorter one. I think I saw you had something about eccentricity on one of the other plots, but I was wondering, like, with these sort of dynamical perturbations that are much closer, have you noticed an appreciable difference when you're maintaining the same semi-major axis or semi-lattice rectum, but varying the eccentricity? Or
Oh, you know what's funny? I told Alejandro, no one's probably gonna ask that question. Thanks for asking that question. So, I frantically, during the beginning of this week, started running tests with this plot, on our dynamic case. And it was interesting that for the same eccentricity, I did get something similar to the static. And I was like, well, maybe my work doesn't mean anything, because maybe the static encompasses everything. It was actually off by like a factor of a few. The big difference was that these eccentricities are sampled from like a contour plot. So you typically see these plots of semi-lattice rectum and eccentricity.
cool
So all these eccentricities are sampled from a set of a semi-lattice rectum. What I found is that for the same eccentricity, I enter another, unmapped contour in their space of resonances. So for the same orbit with the same eccentricity, it just has a different semi-lattice rectum. And so yeah, we can account for a much broader range of those eccentricities of semi-lattice rectum that the static case currently just works in at the moment.
Okay, thank you.
Let's thank the speaker one more time.
Mahalo, everybody.
All right. Yep, that looks good. So our next speaker is Zach Nasipak, who will be telling us a bit more about View.
Yep. All right. Hello, everyone. First of all, thank you to the organizers for making it possible for me to present remotely. I'm sorry I can't be there, but I'm glad I'm at least able to attend from afar. For those of you who don't know me, I'm Zach. I'm a postdoc at the University of Southampton and one of the core developers for FastEMRIWaveforms, or FEW, which has been presented a few times or talked about a few times this week, and initially presented by Michael Katz on Monday, who's one of the original developers for this. But in case you kind of missed that and aren't sure what FEW is a code that leverages kind of techniques from multi-scale self-force that Niels Warburton talked about yesterday, and GPU hardware acceleration to basically simulate EMRIs, like the one on this title slide, in milliseconds, including their gravitational waves. And really a big pillar of FEW is to create a code base that is fast and super accessible so that it can support LISA science and LISA data analysis. So last year we presented the model that was kind of just shown of eccentric binaries, but that are non-precessing and have rapidly rotating massive black holes. And this model has been very productive, but we understand that FEW is currently limited still in the amount of parameter space it covers, how accurately it covers the parameter space, and additionally, how flexible the code base is for actually being incorporated in realistic data analysis pipelines. So over the last year, there's been a large team of people, which I'll call the FEW development team, that have been working on releasing and designing a lot of new models with a lot of new physics within FEW, and that will be released over the coming months. So really, today I'm going to present what is a huge collaborative effort. So in the stars here are the original developers of FEW, and since then there are now 27 members who have been contributing to the code base, spanning 15 institutions, maintaining 10 to 100,000 of lines of code. And what I'm presenting is the culmination of a lot of work by all these people. If you're excited by the kind of science you see today and are interested in getting involved, we're always looking for new members, so please email me or any of the other core developers, and we're happy to see and discuss how you can get involved on the development team. So with that, what I want to talk about are some of the models that we'll be releasing in the next year. I guess it was risky doing a bunch of animations on a remote talk. Hopefully this isn't too laggy, but what you can see are a host of different models. The top left are the eccentric, kind of an update to the eccentric model released last year. Also be talking about a highly eccentric model where you go to kind of these super high eccentricities with bursty kind of waveforms. We'll also be introducing a precessing waveform. So now you have spin-orbit coupling that causes the orbital plane to precess. We're working on kind of the grand vision of having a precessing eccentric model. We do expect to release that in the next year. I just don't have any nice results to show today. And moving down, there's also a suite of models that will be incorporated into few that were actually published in other parts of the literature. In fact, Niels talked about a few of these yesterday as part of the M2SF collaboration. And we're now folding those into few so that they're easy to incorporate into your kind of studies or for people to use who are very familiar with the few software. All right, so first off, I'll just talk about the eccentric model and why we need to improve it. So if you're not familiar with the current eccentric model, let me just lay out kind of the parameter space it currently covers. So the chi1 here represents the spin of the massive black hole, or the primary. We can cover spins up to about 99.8% the maximal rate. And we can cover initial eccentricities of the binary out to about E of 0.85. But there's no precession. So X here kind of measures cosine of the inclination angle or cosine of the precession angle. So when that precession angle is 0, we're talking about equatorial non-precessing orbits. So few's great. It can produce this 3-year-long inspiral just fine. But if you look at the beginning of the inspiral and the waveform, you'll see that there's this ringing in the waveform. And this is not physical. This is actually coming from how we construct the waveform. And so the way we construct the waveform is as a sum over modes, where we sum over LM modes, which correspond to the angular spherical harmonics, and then an N mode that is kind of like a Fourier series over the radial frequencies of the orbit. And essentially, you're getting Gibbs ringing here, where we haven't included enough high frequency mode content to resolve the waveform in this part. So one way that you can see this is that you can actually kind of plot the mode space. So on the bottom axis, I have all the L modes you could include, the y-axis, all the N modes. And the modes that we originally included in the model are all in this red box. And so when you ask Few to generate a waveform, you can ask it just to include all the modes in this box to produce it. Or you can ask it to do something more clever and say, basically include all but the modes that contribute only to 1% or 10 to the minus 2 of the power, or 10 to the minus 3, or 10 to the minus 4. And this threshold parameter actually turns out to be really close to the mismatch you would get if you compared it to a model that included all the modes. And so if you kind of go and evaluate the model at these different types of threshold values, you can see that the dark red here is throw away everything but the 99% of the power. Okay, that all gets included in this box. But as you try to include more and more power, you ram up against the high end edge of this. So we realized we need to include more modes. And if you include all the modes that are in this green space, you see that, when you rerun the model, yes, it wants to include all these higher N modes, even some higher L modes. And the orange curve here is what you get when you include these higher modes. So you can see that the ringing gets resolved. And so this is just for one orbit. We've done this in the investigation kind of for all the astrophysical orbits we might kind of expect LISA to see. And this is the mode space that we realize that we really need to include in the model if we want to accurately resolve the waveform across this total model parameter space. So that's something we'll be updating in the next few months. Now, while we go up to E equals 0.85, it's kind of a conditional statement. So here are some plots of basically that show you the amount of parameter space we cover as a function of semi-lattice rectum P on the bottom and orbital eccentricity on the top. And you can see that especially at high E, low P, there's a lot of white space. It was just too hard when we first designed the model to cover this area. Unfortunately, it turns out astrophysicists really want to have waveforms in this area parameter space. And there have been studied formation channels that suggest that a non-negligible amount of EMRIs might evolve through here. So we wanted to design a relativistic model that can actually test, something evolves through there, is it actually detectable with LISA? So this required kind of like actually reworking how we generate waveforms in the high eccentricity limit. Unfortunately, I don't have a lot of time to talk about it because I want to get to all the other models, but the gist is we created kind of a toy example, or not even a toy example, a simplified example where we restrict to non-spinning binaries, so neither black hole spinning, and using kind of information from scattering theory, parabolic limits, and additionally by mapping kind of the normal gravitational wave phase to like the mean anomaly, and using that as a phase parameter, we were able to tile the parameter space in terms of like fluxes, frequencies, amplitudes, basically from E equals 0 to E just basically equals 1. Though E equals 1, it just sits there forever, so it's not very interesting. So with that, we can produce highly eccentric orbits, like the one here on the left, where you get these bursts that become smaller and smaller separated in time as the orbit slowly circularizes due to gravitational wave emission. And what's interesting is small little changes in your initial radial phase can lead to kind of really big mistimings between these different bursts, as shown in this middle plot here. All right, so that's all about eccentricity, but of course we know EMRIs can also precess. So we've been working on a model that also includes the effects of precession. Now, just to start off, we now are restricting to add precession but throw away eccentricity. Again, we measure precession with this angle, or this parameter xi, where plus or minus 1 refers to prograde and retrograde orbit in the equatorial plane. We cover all astrophysically relevant spins. What I'm going to show you is some kind of interesting physics we've learned from producing this model. So what I'm going to run is an animation of an orbit that starts off as being slightly prograde but nearly polar. And on the right here is showing the evolution of kind of this cosine inclination angle. And you can see, okay, it approaches 0, which would be the polar limit, crosses it, and then goes to negative values, which indicates that the orbit is becoming retrograde. And we find that across the entire adiabatic regime, all the way deep into the strong field, the time rate of change of this inclination parameter is always less than or equal to 0. So things are always trying to evolve to be more retrograde, which is kind of interesting. Additionally, this causes actually problems on the waveform modeling side, because if you're familiar with EMRIs, right, you like decompose the motion in their waveforms with respect to their 3 frequencies, the radial, polar, and azimuthal frequency. And usually you choose those frequencies so that in the test body limit, they match geodesic frequencies. But the problem is, as you go across the polar kind of limit, the azimuthal geodesic frequency is discontinuous, which is really bad for modeling. It's bad to try to drive equations of motion with something that's discontinuous, that has a computational cost. And additionally, we decompose the waveform into modes that are decomposed with respect to this frequency. So anything like amplitudes that get decomposed with it are also will become discontinuous. So we had to kind of remap to a different frequency, notion of frequency, which I defined below here, which is this blue curve, which you can see is actually continuous across the entire inspiral. So that's kind of everything for eccentricity and precessing. What I do want to mention is that there's also been a lot of development in going back to the quasi-circular limit and trying to include more physics or more accuracy there. So Niels, Warburton yesterday talked about efforts in Cellforce to really accurately model quasi-circular inspirals that include small spinning primaries, a small spinning secondary, and what they find is when they compare to at mass ratios of like 1 to 8 to numerical relativity, they agree remarkably well with those waveforms. So we have now incorporated that model into FEW. And additionally, going beyond just the inspiral regime, we've now are incorporating models that go all the way to merger ring down. So you can see here you have an orbit that evolves at p of 10, keeps going, passes the last stable circular orbit, past the light ring, and then kind of gets right to the horizon, and you get this ring down in the waveform. So that's kind of a lot of the models that we've been working on. Now, to make these possible, it actually required rebuilding FEW from the inside out. So the last version of FEW that we released, we called FEW version 2. A lot of these models will now be built on FEW version 3. Which the idea is to make the code base a lot more flexible, to make it easier for people to build models, or to take these models and add in their own effects like resonances, environmental effects, beyond GR corrections. And additionally, we want to expose more information to make it easier to integrate the FEW into data analysis pipelines. So here come the features. I don't have a lot of time. I'm basically running out of time, so I won't go into too much details. Ask questions if you want to learn more about them. But let me just end with saying, okay, so these are the types of models that we have. They'll be released in kind of the next 9 months to a year. Here's our predicted timeline for their release over the next few quarters. If you're interested in using any of these models before their release, please get in touch with us and we can talk about kind of interesting science that we might be able to do with it. And we're always looking for people to stress test these models before we release them to the public. So thank you for listening. And with that, I'll take any questions.
Thanks, Zach, for the nice talk. Any questions?
Thanks, Zach. So these time frequency models, they're all already going to be available in October?
So we won't be producing explicitly anything in the time frequency domain. Part of this is because what that means, there's not like a unique choice for that, right, of how you decompose with respect to time and frequency. So instead, what we'll do is we're gonna give better access to sparse representations of the waveform. So that's kind of this bottom right plot. So essentially we give, it produces these kind of sparse samplings of the amplitudes, frequencies, and the amplitude evolution, frequency evolution across the orbit, across all these modes. And we'll basically give you access to those so that you could easily assemble it into whatever time frequency kind of formalism you want to use.
Hey, Zach, it's Jeremy Schnittman here. I'm intrigued by these highly inclined orbits. Is there like a critical surface where on one side it evolves towards prograde planar and the other way it goes back, or is there like one region where it gets stalled, or what are you seeing?
So basically the only stable configuration is if you start off completely prograde equatorial, and as soon as you move from that, that X parameter decreases over time, no matter what, no matter where. I will say this effect is really small. If you, so maybe if you're familiar with PN, there's been a lot of, they know that when you evolve things early in the inspiral, the precession cone between the orbital angular momentum and the total angular momentum opens up over time, very open early on in the inspiral. And that's essentially what's happening here. What we're just seeing for the first time is that it happens all the way up to like basically the transition region, which I kind of didn't expect. Yeah, you would think like things would get driven back towards being prograde, but no, it just, as soon as it moves off, it wants to become more retrograde. But it does it really, really slowly. So like for an EMRI, it'll go from being like 0.9 to 0.8999 over a year. So it's really small evolution.
Any other final questions? One more.
Okay, since I saw that you're including the JAX backend, are there plans to include auto-differentiation in FastEMRIWaveform? Because that would be very useful for data analysis. I don't know if possible.
Yes, so I would say probably in the initial release, no, just because it would require like porting over a lot more of the waveform interface to JAX. And so I think it's more of we're going to make certain parts of the waveform evaluation available through JAX for constructing the waveform, but I think you'll eventually get to layers of code that aren't completely compatible with JAX. I mean, it's the goal for the future, but that's a huge rewrite.
Okay, let's thank the speaker one more time.
Okay, great.
Next up, we have Curt Cutler.
I'm going to be describing recent work that Mahu Bustamante and I have been doing on a new detection statistic for EMRI searches. I'm going to show you that this new statistic is considerably more sensitive than the usual matched filter statistic, as long as you're not very close in parameter space to the right parameters, or the true parameters of the signal. Before I define the statistic, I'm just going to send several slides motivating it. And if I do a good enough job, then when I finally do define it, I'm hoping you all say, oh, that's obvious. Okay, this figure is the first motivation. And, sorry. And what I want to show here, imagine you've got one template signal and one source signal here in blue and a template signal, a chirp, both chirps. And imagine that the signal to noise of the template against the source is, small but non-negligible. Then I'm going to claim that typically what that means is that the frequency tracks of the two signals, the real one and the template, cross at some point in the FT plane. And almost all the signal noise will accumulate near that crossing time. And the reason should be pretty obvious. At that time, they have the same frequency, or nearly the same frequency. And so for a little time, they're sort of they're oscillating at the same rate. And so the signal noise can increase secularly. So that's an important picture. OK, and based on that, I'm going to define a parameter lambda equals the difference in the f dots of the two signals divided by the common f dot, the average of the f dots. And that lambda is going to be helpful. It'll be a way of parameterizing how far the template is from the true signal, this lambda. And the claim is, I'm going to claim, it's easy to show, that the signal noise you accumulate is exactly the same as if the two signals were perfectly matched for time t coherent, where t coherent is just 1 over the square root of lambda f dot. And I'll just put in some numbers so you get an idea of what this means. Imagine f dot is a signal that moves 5 millihertz in frequency over a year. F dot is 5 millihertz over a year, and lambda is about 0.1, meaning the parameters of the template are about 10% different from the parameters of the signal. Then t coherent is about 3 days. And if rho signal is 20 in that band, then what you'll accumulate and accumulates over a year, then the phase maximized match filter amplitude is just that 20 times 3 over 365, because it only accumulates for 3 days over 365, which is about 0.16. And so when I said at the beginning, small but non-negligible, I was thinking like 0.16. OK, this is perhaps the most important figure in the talk. So it's the same figure I showed you 2 slides ago with the signal and the template, except now I've added one more, this yellow figure, this yellow curve, which is simply the red curve shifted over in time. The template, it's a new template, but it's the old template just moved over a little bit. And the thing I want you to notice is the yellow curve also crosses the blue curve, right? And you can tell by looking at it that the difference in the f dots here is about the same as the difference in the f dots there, meaning that template will also give you a row match filter of, say, 0.16. And hopefully you can, and by the way, it moves over in frequency. When you move over delta t in time, it moves over in frequency by f dot times delta t over lambda. So I think you can see at this point that if you took a bunch of, take one template and now a bunch of time translations of it, there'll be a region in time translation space where you get a fair response. Small, but it adds up over many, many time translations. And by the way, it's easy to numerically demonstrate this. This is a simple example that sort of proved the usual rule that proved what we thought. Here we just took 2 polynomial chirps, have their lasting about 30 days. Their parameters are about 1% apart. You take the match filter of 1 with the original signal and then all the different time translations, and you get this excess in time translation space that I guess it was 0.1. I guess it was 10% different. Excess in time translation space, where you get this considerable excess. So the idea is to calculate all of the inner products with all the time translations and look for a region of excess in time translation space. And fortunately, that's really cheap to do because of the well-known FFT trick. If you have one template, the computer power necessary to find the inner product of that one and all its time translations is just a little bit more than the first one by itself. So even if you have 10 to the 6th time translations, the extra computational power you need is just a factor of 40 because you use the FFT to do it. So the statistic we will do is we'll take one template, calculate the overlaps for all discrete time translations and look for this excess, something that looks like this. Okay, now finally we're able to define it. So we're looking now for a window, basically, in time translation space where there's an excess. So let me just explain the different terms here. So I'm going to calculate the overlap squared at every point using FFT, every time translation. And I'm going to subtract 2 just because I want to take out the average. That's just so I get the expectation value equal to 0 if there's just noise. I just like that. And then I'm going to multiply. Then I have these extra factors, which I'll explain. So if dt is the sampling time, then I want to normalize it somehow. And the basic reason is, imagine your sampling time was really, really tiny. Then the inner products of all the time samples with noise will be won't be independent, it'll be very correlated. So I need some factor that sort of compensates for that correlation. And also I want the RMS value of this statistic to be 1 and its expectation value to be 0, and that's ensured by this extra delta f to the 1/2 and this square root of 4n. So before this maximization, this thing has an RMS value 1. Okay? So I'm going to look for excesses of that in terms of both the location in time frequency, in time translation space, and in width. And now, next slide after this, I'm going to compare the sensitivity of the statistic X with the usual match filter rho. But before that, I just have to make sure you understand what I mean by the SNR of each one of them. And so if your statistic is the absolute value of rho, which is the phase maximized rho, then its RMS value, then it's a Gaussian, or the right half of a Gaussian. And the RMS value is square root of 2. So the SNR is the value you get from the actual inner product with some embedded signal divided by the square root of 2. And X is the same thing. The SNR is what you get just from the true signal alone divided by the RMS value with the noise, except the RMS value with the noise is just 1, so the SNR of X is the value of X. Okay, now a back of the envelope calculation of the sensitivity gain. So just from the equations I have above, you can say that the ratio of the two SNRs, the SNR of X over the SNR of the phase maximized match filtering statistic, well, it's going to go like rho MF itself times the square root of the number of independent time samples in this window, divided by the square root of 2, which from the square root of 2 and the factor of 4 before. Okay, where the number of independent time samples you can show is just the total number of time samples times this factor, the time spacing, times the bandwidth. Those are the number of statistically independent time samples. And that means, and this is just then lambda, you can show, times the bandwidth, I sort of call it the delta F, the other delta F, times the length of the signal. So let's put in numbers. I'll use the same numbers for an example that I used in like slide 2 or 3. Imagine a chirp whose f dot is 5 millihertz over a year, that lasts about a year, and has signal noise of 20, and lambda is 0.1. And so we figured out for that the match filtered SNR for this usual statistic is 0.16, remember that? So then this factor is 0.16 times the square root of a pretty large number. There'll be basically almost 16,000 independent time samples that give you a large amplitude for this value of lambda. So you multiply 0.16 by roughly the square root of 16,000, divide by the square root of 2, and you get 14.2. So it's 14 times more sensitive, 14 times more SNR than what's called the optimal match filter, which is only optimal if you're really close to the right parameters. And it's 1.6 compared to 0.11. And note, or I'll tell you, but if you, from the slides, if you had them in front of you, you can see that this rho MF scales like lambda to the minus 1/2, while this number of independent samples to 1/2 also scales like lambda to the plus 1/2. So this factor of 14 improvement would be the same over almost all parameter space, except when you're very close to the true signal. Or so far apart that the overlap is basically 0. But for a huge region, it'll be about a factor of 14 improvement. And by the way, it gets better if the embedded signal is stronger, because then rho MF will be stronger, larger at any point parameter space. So if the embedded signal had signal noise of 40, not 20, then rho MF would go up by a factor of 2, and the improvement over the match filter would be not 14.2, but 28.4. So this improvement is very robust. Okay, how much time do I have? Okay. So just a quick thing on implementation issues. So again, the first thing you do is use the FFT to calculate rho j squared at every time point. And then to calculate these things, you have to do some arithmetic, and I'm going to argue you can do it quickly. So we have a lot of sum over this of windows. So you start by just computing, and this is a misprint, computing the cum sum of, not rho j squared, but I meant this thing, absolute value of rho j squared minus 2. You compute that once, store it, and then all these windows, all these sums from I to I plus n, are just the difference of two cum sums. So that's cheap. How do you maximize over n? Well, we found by experimentation, you don't have to maximize over all the n. You can maximize over like 7 of the n that are uniformly spaced in log space. So start out with something like 1/10 the total number of n, then that divided by 4, and then that divided by 4, and that divided by 4, and that works fine. So it's like, so you calculate this windows for like 7 different window sizes, and that's good enough. And you might think that now, because of this discrete definition, you choose the maximum using over which n, that the function can't be continuous, but it is continuous. That's not so obvious. But the way to think about it is there's some region given a real signal, and then this thing we calculate, there's a region where n plus I plus 1, say, gives the highest number, it maximizes it. Be some other region in parameter space where ni maximizes it, but there'll be some boundary between them where they give the same number. That's the definition of the boundary. And so everything will be continuous across these boundaries, so it's actually a continuous function, despite this kind of discrete definition. And that's good because a lot of optimizers work best on continuous functions. So that's important. And now the summary. So we've motivated and defined this new statistic that's considerably more sensitive than the optimal match filter when you're far away from the correct parameter values. Maho and I are finishing a paper on these ideas and the application to a simplified EMRI model. So I've skipped over a lot of details, but they'll be coming out very soon. And just as a remark, it may be obvious that very little about EMRIs was concerned here, right? It was just a chirp. So a lot of these ideas should be applicable to so any search for weak, long-lasting chirps. It's just, for us, the EMRIs were the most urgent one. So thank you.
Thanks, Curt. Any questions?
Yeah. The strategy you use is like using one harmonic, right?
So things I've said, just to make it very simple, I used one harmonic. And often, for a lot of EMRIs, one harmonic dominates. But the same thing you can do with 3 harmonics. You just have, say, 3, or any number, really. But it'll be most sensitive if you like 2 or 3, 1, 2, or 3 harmonics. I can explain why. But it certainly works with a set of harmonics.
Scaling goes with n times the number that you put there, right?
Yeah.
Any other questions? Have you looked at using a full EMRI waveform with this approach, or?
We've done somewhat tests like that. Let me just go back. So early on, Aaron Johnson. So it's sort of a mini result based on the second or third slide, that as you go far away from the true waveform, some distance d, and say in parameter value or along a geodesic in parameter space, then after the initial sort of very rapid fall off, the fall off should go like lambda to the -1/2 or distance to the -1/2. So it's actually very gradual fall off as you get far away. And Aaron Johnson plotted this up, and even 2,000 sigma away from the right value here, and so in the A parameter, they're still at 1% overlap, right? And that's generic. It's always this lambda to the -1. So we've tested that works, and we've tested it also for simplified EMRIs, and we've looked at pieces for real EMRIs, but it all looks good.
Let's thank Curt again.
Okay.
Next we have Lorenzo, please.
Thanks. Hello, everyone. I am Lorenzo Copparoni. I'm a PhD student at SISSA. And today I'll present this work that we've done together with Rohit Chandramouli and Enrico Barausse about a consistency test for EMRIs. Now, as we've been discussing a lot, EMRIs are events which hopefully we'll see in the LISA band, in which we have a high mass ratio between the primary and the secondary. And the nice thing about these kind of events is the fact that, of course, the frequency evolves pretty slowly. They are very multimodal, and due to all of these facts, they spend a lot of cycles in the LISA band. Now, when you sum up all of these characteristics, you have that when you do parameter estimation with EMRIs, you have that your posterior are resolved to an exquisite high precision. Now, this is both a blessing and a curse, because, of course, since you have something which is extremely precise, if you put a slight modification to the inspiral evolution, what will happen is that your template, which maybe doesn't include it, will not be compatible anymore with your data. Now, where do all of these possible small effects come from? Well, we know that these kind of events live in astrophysical environment. So the main candidate, the obvious one actually, would be an interaction with the environment, and there is a plethora of possible effects, and these have been studied in the literature a lot. But also you can have that gravity isn't right. You can have a bunch of modification to gravity. Now, if you start to think about this, you can put on a lot of templates, and if you go to someone doing the global fit and you tell them, hey, put 10 templates in your global fit for EMRIs, they will laugh at you, rightfully so. And so, including something which represents all the possible physics that you can have is impossible. So we consider now, let's say, a worst-case scenario in which we don't have anything which allows us to consider modification to, let's say, our vacuum waveform. So we only consider vacuum effect. Now, we have our data in which some events are undergoing some dephasing due to environment, modified gravity, whatever. And we know that if we try to do an analysis with a template which is not accurate, we'll have some signal left in the data stream. Since we have this signal left in the data stream, of course, we will have biases, which we can estimate, for example, with the Cutler-Wallis-Naive formula at a linear order. Now, there is a couple of things that we need to think about, though. These are very, very long signals. And if we have an effect which is unmodeled, the dephasing between the correct waveform and the template one that we use will grow for a longer and longer observation. And lastly, if we think about any physical effect, the contribution of the dephasing is not uniform throughout the inspiral. For example, if we think about something coming from the environment, it comes to reason that the interaction with the environment will be weaker when you are close to the plunge and will become stronger when you are far away. So ideally, if you do an analysis with something which is very close to the plunge, you shouldn't have any bias. And if you allow it to, if you go back in your data stream and you look at a longer inspiral, you will have that your maximum likelihood point moves. So this is the basis of the test that we developed. Effectively, we consider a given waveform, and we observe it with different, we study it with different observation windows. In doing this, we always include the last stages of the inspiral, effectively, let's say the plunge, because an EMRI signal is still a chirping signal. So a lot of the SNR is stored here. And we do a full Bayesian analysis with this difference of the observation window. And in principle, if we find that our posteriors are all compatible with each other, that's all nice and good. Our template is correct, and we are happy. If they're not compatible with each other, there is probably something else that we haven't modeled. So to test this, we consider a simple deviation, a simple power law, which is very physically motivated. A lot of effects can pop up as a power law. Specifically, in our analysis, we consider the -8 post-Newtonian term, which is what you would have if you put your EMRI in a Shakura-Tsunayev disk and you consider only the Newtonian planetary migration. So we did our analysis with this event, with 10 to the 6 mass of the primary, 50 mass of the secondary, highly spinning, and we observe it. We consider an inspiral of 3 years, and we fix the distance so that we have an SNR of about 100, which is high but not unreasonable. And when we do parameter estimation, we see that for a short observation window, like half a year, we see that indeed our posteriors are in the correct position. And as we observe it go back and back in the spiral, they move away, they drift. So that the estimation is biased, but more importantly, if we look at it, these are the 50 and 90% confidence interval, we have that posteriors at 2 years are completely incompatible with the one at half a year. To be sure that this effect cannot be popped up by noise or something else, we repeated our analysis with noise in injection in vacuum and noise, and we tried also to turn on and off the noise in our environmental injection. And we see that the green one is the vacuum injection. It's always nice, compatible with, regardless of for how long you observe it, while, as mentioned before, the environmental one drifts away and becomes more and more incompatible. Now, this is nice, these are nice, pretty pictures, but maybe we would like to have something more quantitative. And so we consider 2 different metrics. And in both of these metrics, we do not consider the full posteriors in a certain sense. We only consider the maximum likelihood point. Our first one, which is a, let's say, 1D test for each parameter, we compare the maximum likelihood, we calculate the distance between the maximum likelihood point at a reference time of observation and for a longer time of observation. And we weight this distance based on what is the 90% confidence interval. Now, this, as I mentioned, includes only one parameter or a small subset of the parameter. Another test would be including all of them. And to do that, we consider the mismatch between the maximum likelihood point at a reference time and the maximum likelihood point at a different time. And in computing this mismatch, of course, we use as an observation window the shorter observation window, which is the reference, our reference observation window. Now, we say that 2 posteriors are incompatible in this latter case when we have that this mismatch, or fitting factor, however you want, 1 or 1 minus fitting factor, which would be more accurate, is bigger than the 90% confidence limit of the chi-square distribution weighted by your SNR. And this is pretty simple to obtain. This value comes from a Fisher approximation of your likelihood. And if we go back to our injection and we look at what are the values, we see that indeed, as expected, for observation longer than 2 here, when we compare our posteriors against the ones obtained for a half-a-year observation, well, we have that we are not compatible in terms with the first test. And on the second test, here I highlighted in red the values for which we get above this threshold. We still have this incompatibility. Now, one can say, OK, there are a couple of caveats. First of all, when we'll do the analysis in LISA, we won't be under the 1% sure on what the PSD is. The PSD will be estimated throughout the global fit. So to check the robustness against this, we try to do an analysis in which we injected vacuum with a noise generated with a mismodeling of the PSD compared to the one used in the parameter estimation. And we tested it with an underestimated acceleration noise component and an underestimated galactic binaries foreground. And in both cases, the mismatch obtained were compatible with the one obtained in an analysis done with the same PSD used for noise generation and recovery. Secondly, one can say, OK, we have this test, which seems to work. Can I have, based on my posterior result, can I have an idea of what is the physical effect? And the answer, sadly, is no, because we just test the inconsistency between the posteriors. Ideally, we can get an idea whether our effect is distributive or not. But ideally, we can identify if in our data stream there is something in model, and then we can use other methods, such as a new analysis or importance weighting, as proposed by Kejriwal, and to obtain the actual physical parameter and maybe do some model comparison between the different hypotheses. And lastly, can we use our reference observation time, the shortest one, as the correct posteriors? One may be tempted to say yes, but is wrong, of course, because let's say if we have an environmental effect, it may come to reason that for the shorter observation time, you have that your posteriors is completely unbiased in some cases. But we are not sure what we will observe. And we may observe, for example, an effect coming from modified gravity. And modified gravity can act at positive post-Newtonian order. And if we try to do our analysis with a positive PN term, here we did an analysis with a 1 PN modification, we have that even for our short observation, the posteriors is completely biased. And we still have an inconsistency between a longer observation and a shorter one. But we cannot say, for example, that this half-year observation is the correct one, because here we have that the phasing term is always the strongest component of the phasing term is always present in a data stream. So, to conclude, we developed this simple consistency test to understand whether in our data stream are present something coming from a model effect, which can be new physics or environmental effects. And this is just first stepping points, and a few future work or questions still remain open. First of all, we did our analysis with only one event in our data stream. But of course, since we have that we are using wrong templates, a small amount of signal is left. Here is the amount of signal left, for example, for the case I was showing before. And for a 3-year observation, we can have up to 7 residual SNR, which is not optimal. And so we should go on and retest these consistency tests with multiple events in our data stream to check if these residual signal interacts with other sources and spoils, for example, other measurements. Secondly, we may, in the LISA global fit, have some, let's say, agnostic templates to try and get information on the environmental effect or modified gravity that we may encounter. But usually these templates are much simpler than what you actually see. And so, for example, it would be nice to test whether this works also if we try to use some simple agnostic template against a more complicated modification, such as relativistic interaction between the environment and a black hole. And lastly, we've done this for EMRIs, but nothing stops us to try and apply this to other long-lived sources, for example, stellar origin black holes, which are much fainter. So this consistency honestly might not work, but it would be nice to test whether we find something interesting in that case. Okay, thanks for your attention.
Thank you very much. Any questions for Lorenzo?
Thank you. Based on your studies, would you say the only way we can confidently detect beyond GR effects is by finding the perfect system to study? So we can characterize it with optical observations, watch it in spiral, know exactly what all the other objects orbiting are, all the systematics, all the sources of error, to be able to control for those and then find the tiny little effects we're looking for. Because the thing about these effects is they're so small, it's hard to know if what we're seeing in our predictions is going to be real or it's just a quirk of how we're numerically processing things. You know what I'm saying?
Okay. Now, regardless, in general, as you mentioned, all of these effects are small. And honestly, when you try to infer the properties of any deviation that you have, the posteriors that you have on any deviation on EMRIs are usually consistent. They give you information, but they are not, let's say, of course, as precise as your result on vacuum properties. So to be 101% sure that your physical effect is indeed the one that you're studying, I don't know, let's say, I'm not an expert on modified gravity, but I don't know, maybe if it's specifically that kind of charge, the question depends on how good the template you use for recovery is, and of course, the SNR of the signal. The more information you have, of course, the better it is. I'm honestly not sure. I'm a bit pessimistic, but I would say that probably what would happen if we just have, let's say, a dark observation, we just say, okay, these are the list of possible effects. And the nice thing about, let's say, LISA is that we won't observe a single source. So if we have something which is a modification of GR, hopefully shouldn't pop up in a source alone. It should pop up throughout your data stream. So more than observation from electromagnetic sources, I would be more hopeful to have something that it's a hierarchical test with different sources. That honestly seems more reasonable to me. So not more reasonable, more realistic. Because for example, for EMRIs, I don't know how many electromagnetic observations you will have at the same time in which LISA is active. You may have something before, like quasi-periodic observation, but at the same time, I'm not sure.
Any other questions? If not, let's thank our speaker again. We have Pankaj. Please take it away.
Yeah, okay. Hi, everyone. My name is Pankaj. I'm a postdoc at Niels Bohr Institute. So in this talk, I will be talking about how to test the general theory of relativity with the eccentric binaries and why the eccentric binaries are interesting for the LISA band. And this work is done in collaboration with Silvan Mirza from L2IT and Johan Samsing from NBI. So if we have an eccentric binary, it will emit gravitational waves, and these gravitational waves will carry away the energy and the angular momentum from the system. And you see that the semi-major axis and the eccentricity of the eccentric orbit is a function of the energy and the angular momentum of the system. So if the energy and the angular momentum of the system are changing, so the semi-major axis and the eccentricity of the orbit should also change. And the evolution of these two quantities is given by these two beautiful equations derived by Peters in 1964. So why these equations are important? So these equations are telling us that in a finite amount of time, your semi-major axis and the eccentricity will decrease, and your orbit will shrink and become circular. And it turns out that this circularization is very effective, as you see from this plot. So if you have a binary with an eccentricity of 0.1, which is emitting at 1 Hertz gravitational wave frequency, and by the time it enters the LVK band, the eccentricity has reduced by 2 orders of magnitude. So the eccentricity decreases very, very fast. And we also see this in the binary pulsar observations. So This is the data from the binary pulsar observations, and this is the present value of eccentricity at this frequency, which is in the millihertz regime. So you see that like a lot of binary pulsars have a significant value of eccentricity at this frequency, but when you propagate this eccentricity to the higher frequencies, which is in the ground-based detectors, the eccentricity reduces by many orders of magnitude. So it is more likely that you will find an eccentric source in the LISA band than in the ground-based detectors. So what are the astrophysical expectations of the eccentric binary black holes? The eccentric binary black holes are expected to form inside the dense stellar environments, for example, the globular clusters and the nuclear star clusters. And because there is a lot of interactions going on, and the density is like millions of times than the solar system density. And if you perform the n-body simulations of these systems, if you perform the n-body simulations of these systems, you get this kind of eccentricity distributions. And you see that most of the binary black holes have the low value of eccentricity, but there is also a peak at the high value of eccentricity. And these simulations suggest that around 5 to 10% of the dynamically formed binaries can have an eccentricity greater than 0.1 in the LIGO band. And in fact, there are potential eccentric candidates of the eccentric binary black holes in the LIGO Virgo data. Okay, so how the eccentric gravitational wave signal look like in the LISA band? So unlike the circular binaries, which emit gravitational radiation only at one frequency at a time, the eccentric binaries emit gravitational waves at the multiples of the orbital frequency. So you see that the gravitational wave is n times the orbital frequency, where n is the harmonic number. It can go from 1 to infinity. And so even for a small value of the orbital frequency, you can have a very high gravitational wave frequency. And the gravitational wave signal is computed by summing over all the harmonics in the band. So if you plot an eccentric gravitational wave signal for the different values of eccentricity, you see that the strain for the high value of eccentricity, the signal is being pushed towards the higher frequencies. And that's because the signal is composed of many harmonics. And if you decompose one of these curves, you get like these many harmonics, and the higher harmonics lie at the high value of the frequency. And that's why the overall signal is being pushed towards the higher frequency band of the LISA. And this harmonic structure is very important for the parameter estimation and the SNR of the signal. So we can compute the SNR of the signal by summing over all the harmonics and taking the inner product. So here the first term is the term which is computed using the diagonal elements of the SNR matrix. And the second term is the term which you can compute from the cross terms of the SNR matrix. And here I'm showing you the two cases for the binary. So the first one is the binary which has 10 years to merge, which is less relativistic. And the second one is the binary which has 4 years to merge, which is like more relativistic. So now we see that the most of the SNR comes from the diagonal elements for the less relativistic systems. And the off-diagonal terms contributes very less to the total SNR. But when we go to the higher relativistic system, then there is a significant contribution from the cross terms to the total SNR. So, and this also means that it also increases the computational cost when you include these cross terms for the highly relativistic systems. So moving to the parametrized test of GR, and which I think Professor Emanuele Berti has already give a brief overview of the parametrized test. So in this talk, I will focus only on the inspiral part of the signal. And the inspiral part can be well described in the post-Newtonian theory. So in the post-Newtonian theory, the gravitational wave phase can be expanded as a power series in terms of the orbital velocity. And these phi i's are called the post-Newtonian coefficients, which contain the various physical effects. And so what we do in the parameterized test is that we deform the value of these post-Newtonian coefficients around the GR value by introducing these non-GR parameters, delta phi's. And these delta phi's capture a particular class of deviation from GR. So in GR, the value of this delta phi's is 0. So if the gravitational wave signal is consistent with GR, then the value of these delta phi's should be consistent with 0. But this is for the circular binaries. So how do we perform the test of GR with the eccentric binaries? Because for the eccentric binaries, we don't have this nice post-Newtonian series, which are the integers powers of the orbital velocity. So yeah, the one motivation comes from the fact that probe those physical effects which are intrinsic to the eccentric binaries. And one such effect is the perihelion precession or the periastron advance. So the observations of Mercury suggest that its orbit precedes by 2 degrees per century, and most of this precision comes from the gravitational pull of the other planets, and some of it comes from the oblateness of the sun. But if you remove all of those effects, there still remains a residual precession, which is purely due to the general relativistic effects. And there were some discrepancies between the Newtonian theory and the observations. And then Einstein came up with this expression, which is a leading order relativistic expression for the rate of perihelion precision. And using this expression, he was able to resolve the discrepancy between the theory and the observation. So just to give you an idea about the magnitude of precision in the different systems, for the Mercury and the Sun system, the rate of pericenter precision is like 43 arc-second per century. And if you go to the more relativistic system, which is the Hull-Stellar pulsar, this precision becomes 4 degrees per year. And if you go to the more relativistic systems, which are the binary black holes, then the precision rate is like 4 degrees per second. So this is an extremely strong effect for the binary black holes. So if you could parameterize your waveform model in terms of this effect, you can test GR with these binaries. So what is the accumulated precision in the LISA band from the different binaries? So we can compute the number of precision cycles a binary spend in the LISA band. And using this, we can compute the number of precision cycles. Again, I'm showing you the two cases. One is the binary which has 10 years to merge, and another is the binary which has 4 years to merge. So you see that the less relativistic system spends hundreds of precision cycles in the LISA band. And when you go to the more relativistic systems, the number of precision cycles becomes thousands, thousands and fives of thousands. And if you compare this number of precision cycles to the LIGO binaries, then these precision cycles are only a few precision cycles. So the LISA provides the best opportunity to probe this kind of physical effects, because the binary spends so many precision cycles in the LISA band. Okay, so now if you have your waveform model, which can be described in terms of the amplitude and the phase, and the amplitude is a function of the eccentricity and the rate of pericenter precision and the other GR parameters. So what we do is that we deform the value of the gamma dot, which is the rate of precision, by introducing this non-GR parameter, a delta alpha. And this delta alpha captures a deviation in the rate of pericenter precision from the GR prediction. And in GR, the value of this delta alpha is 0. And then if the delta alpha is positive, that means that your rate of precision is faster than the GR prediction. And if delta alpha is negative, your rate of precision is smaller than the GR prediction. And then we ask the question, how consistent is delta alpha with 0? So this is like a more relativistic version of the perihelion precision of Mercury and the binary pulsar test. Then we perform the parameter estimation, and to perform parameter estimation in the LISA, it's very crucial that we have to take the full LISA response into account for the accurate parameter estimation. And to do so, we use LISA beta, which is a software package that computes the LISA response. And yes, we get these kind of posteriors. So you see that the delta alpha posterior is here, the accuracy is of the order of 10 to the power minus 4. And these bounds, so this is like a very, these bounds are comparable to the pulsar bounds. And so this is like an extremely precise test of GR with these kind of sources. And this is just for only one eccentricity, but if you perform the same test for the different values of eccentricity, because the eccentric binaries have larger precision for a given orbit, so here I am showing the delta alpha posterior for the different values of eccentricity. So you see that as the value of eccentricity increases, the posterior becomes narrower and narrower. And that's because the eccentric adds more harmonic structure to the waveform. And that helps in breaking the degeneracies and gives you the better bounds. So yes, so Lisa will enable the precision test of strong field test of GR if we find these kind of systems in the Lisa band. And so just to conclude, because this test cannot be performed with the ground-based detectors because we don't have like many precision cycles in the ground-based detectors. So Lisa gives us the best opportunity to perform this kind of test. And with that, I would stop here. Thank you.
Thank you. Any questions?
I think I'm missing something on your last slide. Could you go over that slide again? It looks like you're injecting something, and by adding higher harmonics, the phase shift goes away. I don't think I'm reading it correctly. Your last slide, that's up on the board right now. Could you go over it?
Okay, can you say that again? I didn't understand.
Could you explain the slide number 12 that's on there?
Yes, so here I'm just varying the value of eccentricity for the same system, and I'm showing the posterior on the delta alpha, which is a non-GR parameter. And as you see that the value of eccentricity increases, the posterior becomes narrower and narrower. The bounds improve because the eccentricity adds more structure to the waveform and it helps in breaking the degeneracies among the different.
Eccentricities, higher and higher harmonics, you're able to bring it more and more toward the true value.
Yes, that's right. Yes.
Thank you.
Yeah.
Any other questions? Oh.
Hi, thanks for the talk. I have a question actually to this slide also. Are these, point one, are these noiseless injection? And if they are, why is the posterior for 0.1 eccentricity not centered at 0?
Yes, because this delta alpha is also correlated with the other parameters. For example, the initial angle of the periastron. So you don't expect to be centered around. I think it's, yeah, it is due to those correlations which do not let this posterior centered at the 0. But when you increase the value of eccentricity, those correlations becomes weak, and that's why you have like the centered posterior at 0.
Nice talk. So you mentioned that the eccentricity will sort of circularize out, but if you were to go into, say, the ring down part of, say, an LVK signal, would you still get this sort of harmonic structure from the eccentricity that you had earlier in the inspiral? Or would that sort of like damp away?
You mean in the LVK band? Sorry.
Yeah, if you had like something that was eccentric earlier on, would those harmonic structure kind of damp away with the eccentricity, or would it still be some signatures there?
You mean the harmonic structure in the LVK band or in the Lisa band? I don't understand it first.
Well, I'm thinking like ring down, so I guess, yeah.
Yeah, because the eccentricity damps very, very fast towards the merger, and I'm not sure because there are no models of the eccentricity in the ring down part. So I think, yeah, I'm not sure about that because yeah, the effect might be very small. It depends on the initial value of the eccentricity, but yeah, it's not very well modeled for the ring down part, I would say.
Doesn't work in a spiral effect. Okay, thank you.
Okay, let's thank our speaker again. Okay, last but not least, we have Cole Miller.
All right, thank you. We have heard repeatedly at this conference of the importance of extreme mass ratio inspirals. However, as we heard in the first day from Savick Ford, the rates of EMRIs are uncertain by a good 3 orders of magnitude. Fortunately, there is a category of events frequently observed, the tidal disruption events, which may at least share in some of the dynamics. So the question is, can we learn about one from the other? And I'm going to tell you about a variety of things, the different channels for each one of these possible events. I'm going to talk about the possible differences in the dynamics, and then the question will be posed, can we learn about EMRIs, which we have not observed, from tidal disruption events, which we have? Something to keep in mind, indeed a central point of this presentation, is that if you have a star that gets too close to a black hole, it's ripped apart and you have an electromagnetic event. But an EMRI is a bit of a trickier thing because you need to add many cycles in order to be detectable with something like LISA. So that's a big issue. I want to thank you for sticking it out to the end of the conference, but I know you may be a little tired. So here are some of the conclusions that you can get. One of those is, if we have our central question, the answer is maybe, but. So it may be that we have enough information that we are going to be able to put together some estimated EMRI rates. But there are some critical differences, including fundamental processes which could be distinct. Something else to keep in mind. First, one is that tidal disruption events come from stars. EMRIs are mainly going to come from stellar mass black holes. They're not the same. The second is that the theoretical and observational rates for tidal disruption events are about 10 to the minus 4 per year per galaxy. The estimated rates for EMRIs might be between 10 to the minus 6 and 10 to the minus 8. There's a substantial gap. So this already should warn us that there are some issues. Let's now talk about some of the processes that can give us these types of dynamics. And we're going to talk first about two-body relaxation. And anytime I give a presentation such as this, I am struck by the occasional difference in language from the scientific purpose and the general public everyday purpose. If you mention to somebody two-body relaxation, they would perhaps think of hanging out at the beach with their partner. But in this case, we are considering a cluster of stars, black holes, what have you, around a supermassive black hole. And the issue is that these individual stellar movements are being perturbed by usually two bodies scattering, typically at a distance, and this can change the energy and the angular momentum of the orbits, leading on occasion to something that plunges to a very small pericenter. And in the case of an EMRI, it can then lose energy and get bound and eventually spiral onto the supermassive black hole. The orbits are going to be spiraling for many, many times. And indeed, this is one of the key issues, is that if in their tens of thousands of orbits, they get enough of a perturbation, they might actually just plunge into the black hole rather than leading to the many cycles important for a detection with LISA. If you have such a process, you expect to have very substantial eccentricity and any inclination at all. It's coming from a large distance, meaning that it has no knowledge of the spin of the black hole. Now, a second process is often called the Hills mechanism, and it was introduced into the study of EMRIs by my colleagues and myself in 2005. And this is binary tidal separation. Suppose that instead of an individual star or black hole, you have a binary, then it can come close to the supermassive black hole. It is, in fact, going to be much farther away than needed to rip apart a star. And you don't even need to lose energy. All you have to do is exchange energy, leaving one behind near the black hole, and the other might be kicked out to be a hypervelocity star. Now this, compared with the previous mechanism, is going to typically give you a much larger pericenter and a much smaller apocenter, leading to circularization and orbits that are not nearly as eccentric by the time that they would enter the LISA band. In addition, this is not going to give you any plunges. If this happens, it's going to spiral its way in and definitely be detectable with LISA. So with this in mind, what can we say about the information that we can obtain about EMRIs from TDEs? I think that I would like us to agree, I hope we can agree, that we can only have a very clear mapping if it's the same channel. Because if it's different channels, then who knows exactly what may be going on. So we're going to begin with the assumption, which I think is reasonable, that most tidal disruption events come from the two-body relaxation channel, coming in from a large distance, small pericenter, and getting ripped apart. Now with this, are we at least going to be assured of some sort of equality between the TDEs and EMRIs? And the answer is not quite. Again, this is, remember, one of the central points I gave you on my second slide. If a star is unlucky enough to venture too close to a black hole, it's getting ripped apart. Maybe it's a partial tidal disruption, but that star is not happy. On the other hand, if you have a 10 solar mass black hole, say, and it starts to spiral in, at typical distances expected for EMRIs, a gigaparsec, say, in order that it accumulated enough signal to be detectable with LISA, it has to go through probably hundreds and maybe more orbits. So it has to be fairly stable and go repeatedly. The TDE is a one and done. So this is the issue. What is the ratio between a true extreme mass ratio inspiral, hundreds of orbits accumulating signal, versus something that goes around just a few times and plunges to be invisible with LISA? Well, that's a challenge. We don't know. I'm not saying it's impossible to know, but we're going to need to know a lot more from observational clues and also theoretical work. There are a few other things that come in, mentioned also by Savick Ford. Triaxiality. Of course, physicists always like spheres, but eventually we have to confront reality. And if you look at the nature of the nuclear star clusters, there is some degree of deviation from sphericity. It could be triaxial, meaning there is no conservation of any individual angular momentum component. You can even go backwards in the same orbit. Pretty impressive. Rotation also has an influence. These are likely to be more important for things farther away, affecting tidal disruption events more than EMRIs, because the triaxiality would be greater at a larger distance. There are other things as well. There's been interesting work by Odilia Tabul and her colleagues indicating that when you have an EMRI which has very, very high eccentricity, strong individual kicks, rather than the gradual accumulation of weak kicks, can have decisive influence, can even kick them out of the orbits entirely. And then there are things like so-called resonant relaxation, which is a similar aspect of resonance that we heard in the first talk, that can secularly change the semi-major axis to a degree, the eccentricity and the inclination. Again, it's not obvious what is important here. What I'm saying is that there's a lot of room for continued study. And then I want to get back to the second mechanism I mentioned. So far, we've been mainly focusing on two-body relaxation. But what about binary separation? So binary separation from the EMRI standpoint has the wonderful advantage that if you've done that and you have a nice high pericenter and a nice low apocenter, that thing is just going to spiral in. No plunges, no fuss, no muss. It's going to give you an EMRI signal. So if it happens, it's kind of a guarantee. It's also, for people who like studying these things, nice because the eccentricity isn't too high so it doesn't kill your template bank. But are there tidal disruption events that actually come from this mechanism? I think we don't really know. Things such as quasi-periodic eruptions, QPEs, may be related to this, but it's a little bit difficult to tell. Maybe if you see multiple tidal disruption events in a few years from a galaxy, that could be related. And then, of course, there are the so-called hypervelocity stars, many of which have been seen in the Milky Way galaxy, heading out of here at 1,000 kilometers a second, likely due to these types of interactions, but it's not clear. With that, here are my conclusions, and I'll be happy to take questions.
Thanks, Cole. Any questions?
So how much is this potential analogy dependent on our understanding of the ratio between stars and compact objects in a cluster?
Yeah, so in terms of the ratio, if you have a relatively low mass for a galaxy central massive black hole, 10 to the 6 solar masses, which is more or less in the sweet spot for LISA, you have the advantage that there's enough time for mass segregation. And that's something where you can have a reasonable initial mass function and fairly well project what the population is going to be. For more massive black holes where there's less time, it should be more dependent on the initial conditions and therefore trickier. So for the 10 to the 5, you've got mass segregation that's going to happen on a very rapid time scale. So I would think that there should be a fairly steady state population.
Any other questions?
Hi. So if we say, okay, the EMRI rate is uncertain by several orders of magnitude, and the TDE rate, or the observations of TDEs are about to really explode in the coming years. So, like, I totally appreciate what you're saying about, that it's very tricky to try to tie EMRIs and TDEs together. But do you think, what is your level of optimism or pessimism about reducing that uncertainty range from several orders of magnitude to, I don't know, a couple?
Yeah, I think here is where if, for example, in the LSST for Rubin, if it's possible to find a category of TDEs or TDE-like events which seem similar to what you'd expect from binary tidal separation, I'd be much happier at making that association, because then you rule out the uncertainties of the plunge to EMRI rate. I think that's a potential big plus from such surveys.
Any more questions? If not, let's thank us. Oh, there's one there.
For the binary separation, do you also get tidal disruptions for larger mass black holes? Because I kind of picture the main sequence star kind of slowly getting closer and closer instead of just plunging right in.
Yes, so one of the interesting possibilities for ordinary stars in such a configuration, the binary tidal separation, is they might actually end up giving you steady mass transfer rather than a disruption. It depends a little bit on how eccentric they are by the time they get to the tidal radius.
So recently, there have been some arguments that say the majority of TDEs might actually come from partial tidal disruptions. And if that happens to actually be the case, would that change this argument about two-body relaxation versus hills?
It's an interesting point. I think that it depends a little bit on whether we think that, say, binary tidal separations can give you partial tidal disruptions, because the normal thing you would expect is that if it's gradually moving in because of gravitational radiation, that it would slowly move into the tidal regime, maybe swelling the star. They're so-called squeezars. And I'm not sure those would look like partial tidal disruptions, but a lot of this is a fairly open set of questions.
Any more questions? If not, let's thank our speaker and all the speakers from today's session.